max height of that ball? Let's talk about that. I'll hit the lights. Isn't that cool though? The aeronautics gonna give them, but they practice that stuff. Sometimes it seems like that's luck, but they practice that. All right. So right now, let's find the max height of that ball. How high did he get? Any suggestions? Oh, what do you think?
Take the derivative, set it equals 0, see the max.
I love it when he's talking about the actual derivative of this. Remember the tangent vector? He says find the derivative vector, the tangent vector, and he said set something to 0. Now there's two components. Which one should we really think about setting to 0?
Y.
Because this one, everyone, do you notice the x component? That derivative, the t just comes off, this will always be constant. He's talking about the y component of the velocity vector, right? That's what this is. This is that velocity vector, aka the tangent vector. He says, go over here to this one, take its derivative, which is just this. You all agree?
Mm-hmm.
Take out that t. What's 2 times a half?
It's 1.
I get minus 9.8t, right? He says take this, set it equal to 0. Good job. All right. 9.8t equals 0, and he says solve for t. What's t equal to? 25.4 sine of 55 divided by 9.8. All right. I'm guessing the whole path took about 4.2 seconds. This should be about halfway, right? Is it? 2 point, something like that. I'm guessing. I'm sure I'll agree. I mean, even though he has 2 meters in height, right? It's just a ball, but it's probably about 2.0 something seconds.
2.123.
All right, and I'll go like this. Now you can store that somewhere. But now how do you get the height? Take this number and plug it back where?
At the original equation.
Yeah, not back into r prime and t, you'll get 0. The same, go back into the y component, don't forget that plus 2. Right? So let me rewrite this so everyone knows where I'm putting that back into. Feel free to type it on your calculator right now. The same, don't put it in here. That's the x component. Say put it back in this one, 25.4 sine of 55 t, substitute there, minus 1/2 gt squared. Substitute it here, use 9.8 plus a 2. Don't forget about that plus 2 meters, right? I'll give it 2 more meters. All right, so when you substitute 2.13 here, and 2.13 there, and square it, and use 9.8, I use the storage button again, so you can just use letter x. And I just type, I store this to x, and then I go 25.4 times sine 55 times x minus 1/2 9.8 times x squared plus 2. All right, what's the max height? This will be in meters.
It's 24.08 meters.
4.08 meters.
0.19, I guess.
Any questions on that? That's how high that ball got. Did you heat? It almost hit the rafters. You can see that in the fans video. It's hard to see that on the TV. It just TV went out of view. Cool. Hey, one more thing. Someone else posted an article. And I say we investigate this. Any light from the bulb? I think so. Make sure the source is the computer. All right. Okay. Yeah, nerd alert. That's the title of this one. Let me investigate this? We hear about all this stuff, like we hear about fake news and all this. Well, look what this guy's saying in this article. Was the next day, you can see it was posted. From Matty Spurts, North Alert. Aaron Rodgers' Hail Mary throw actually traveled what? Almost 100 yards. They're talking about the actual what? Arc length. Can we investigate that? I love it. What can we use? We just learned it today. Like the curve. Sound good? Let's try it. We'll use a calculator. We'll just see. Did it go actually 100 yards? Yeah, we know meters and yards. There's a little conversion in there. I mean, there's like 1.09 yards in 1 meter. So when we're done, we'll keep everything in meters and just convert it back to see what the yards is. See if it hits that 100 yards. Sound good? So we gotta do this. Go ahead and try it. I'll write on the board too. We're gonna challenge this article that his Hail Mary actually traveled almost 100 yards. Well, he has the word almost in there. But is it close? We'll see. I'm gonna write this out. So I need R prime of t, and then I need the magnitude of it. Okay. All right. What was the R prime of t again? 25.4 cosine 55. And what was this? 25.4 sine of 55 minus 9.8t. And my limits of integration, we have to know the time it took from the earlier problem. Let's go up to 4.21 seconds. That's what we'll do. So let's go 0 to 4.21 seconds in a year. Square root of, okay, be careful typing those in your calculator. Square that. The calculator automatically puts a parenthesis on my square root. Does it do it with yours? So I'll let that be there, and then you're like, now square this guy. 25.4 cosine of 55 plus square all this. 25.4 sine 55 minus 9.8. You want to just use the variable x off the calculator? I'll put a dx here for that. Just because most people just use letter x off the calculator. Just be careful with the calc, parentheses, and we'll see what you get. Did it go 100 yards? So now keep in mind, our answer is going to be in meters, right? So I just want to get set up first. But when we're done, can I just multiply by 1.09 to see if it went 100 yards? I'm just challenging this guy. Nerd alert. All right, when you know your mathematics, and we get something. What'd y'all get? Putting all this into the Math 9 of the TI-83 or 84 calculator. Let me get something. I'll make sure you're in degree mode, right? Switch it to radian instead of degree.
So I have a crazy answer.
It's crazy though, because this is radian mode, and then this section's all degree mode. Alright, what'd you get?
I got 500. I had it in radian. I forget.
See, do you know what this? Hit the second enter button, see if that works. I'll tell you what I got. When I typed all this in my calculator, I got to be about here. Right about that. But then I gotta multiply, what is it?
1 point.
So how many yards is that? What's 78 times 1.09? It's not 100. Yeah, it's about, what, 85 yards? So that's what I'm getting for the arc length, right? Almost 100 yards, okay. I know. Yeah, but you're 15 yards off, right? Cool. Isn't that neat? You can really explore this stuff and find the actual length of it. It's kind of cool. All right. Hey, I wanted to do the problem that was in the textbook, and it had X, Y, and Z components. So I'm going to do that now. Then we'll come back and look at some more of these problems. So we're talking about an X and a Y and a Z component for this. So this is from the textbook. I'll give you the page number 2. This is in 13.4. This is number 31. And 13.4. So what they told us was, here's what they gave us. They said the initial velocity is, they give a vector, 50i 80k. 50i plus 80k. You okay if I write that in component form? 50i 80k, so what's the y component? 0. I'm just going to put it like that. They wrote it in standard basis form. They said, oh, the spin of the ball resulted in a southward acceleration of 4 feet per second squared. And the acceleration as, and here comes A of t. This was given. The acceleration was negative 4j. Get all this out of the way. Negative 4j. Negative 32 on the k component. So what's the x component?
0.
0. Alright. There's all the information about the ball. What's the question? Where does the ball land and with what speed? Where does the ball land and with what speed? And they did indicate in this ball, the ball is thrown eastward into the air from the origin in the direction of the positive x-axis. So if you want to know when we're saying, alright, here's the positive x-axis. The ball is being thrown in this direction, towards the positive x-axis. Well, they want us to figure out where does the ball land. Let's just go get position. Sound good? Let's go get position. And when the z component is 0, it's going to be on the ground, right? It'll be in the xy plane. All we got to do is get to r of t. All right? What's v of t? What's the velocity vector? Well, I'll just put a c for constant here. What's the integral of negative 4?
Negative 40.
All right, plus constant. What's the integral of negative 32?
Negative 32 plus c.
And 32t plus constant. What's the constant for v naught? This was a what? 80? What's this constant?
0.
0? Maybe I should put the plus c's first, then I'll put all the constants. So I'll do that. Let me write it again. V of t is now, because v of 0 equals these three, in terms of the initial velocity vector, that's a 50. That's a negative 4t plus 0. And this is negative 32 plus e. All right, what's r of t? All right, here comes position. This is the position. 50t negative, what's the integral of that? Is that 2t squared? Now what's that? This is the one we're worried about. Negative 32t squared over 2 plus 80t plus constant, right? Now all these have plus constants. I'm just not writing them because they said it was thrown from the origin. So if it's thrown from the origin, this will be just what? 0, 0, 0 for each constant. So I'm not even writing the plus c's. They said it was thrown from the origin. Plus 0, plus 0, plus 0. Now, where does ball land? It lands when, which one of those is equal to 0? It used to be the y component when it was two-dimensional space. Now we're talking about, when it was two-dimensional space, just thinking about ball went straight like that.
c equals to 0.
This is what we're going to do. Take that guy and set to 0. And that means it'll be sitting in the xy plane. All right? Negative 16t squared plus 80t equals 0. We can factor that. We can factor out of that.
16t.
You're left with negative t plus 5. All right, there's 2 times. It's when t equals 0. Yeah, when it's thrown from the origin. What's the other answer?
5.
We know exactly, everyone, at 5 seconds that ball is going to land. 5 seconds in the air. Let me go back to the question. We'll see if we really answer this. Where does the ball land? Oh, they want the actual point. They want the XYZ point. So where can I plug this into?
On x.
Go back to R of t and just plug it right back into the position. It'll give you the position at that point. So what's that position? 50 times 5? 250. Negative 2 times 5 squared. And what's negative 16 times 5 squared plus 80 times 5? I think I should know that, because I was just playing around with that. what should be the z component? It's gonna be when it's on the ground, so this
Zero.
should turn, when I plug it in here, I should get what?
Zero.
Zero. I did do those right, didn't I? Lucky, I get you back here. There's little errors, forget the parentheses. Is everyone okay with that? Something else I want us to explore in this section?
Should we not put it on vector component form or just?
I'm gonna write it as a point.
Okay.
Great question. The way they've stated the question, Art, they wrote, where does the ball land?
Okay.
I'm like, okay, well, I'm just gonna draw an actual point in the XYZ plane. That's sitting there, right there. That's where it's gonna land. Took 5 seconds, right? These next two problems, I want us to explore these. I actually put problems like this on the practice set. This is like number 25 and 27 from the textbook. This is in 13.4. Oh, piece of cake. We know how to deal with this, right? Just explore things. In these two particular problems, I want you to understand that they gave us only limited information. They maybe gave us the initial speed, maybe the angle. They didn't give us as much information as before. So for those two problems, I was wondering if we could create another formula. I do want to point out in both these problems, it was launched from the origin. Okay? So I do want to say it was launched from the origin. And we can just think two-dimensional space. I was just wondering if you could help me derive another formula that will make these problems much easier to solve. Okay, so I'm going to start out. What was our thing? We're just going to derive one more formula.